or elimination. So a linear combination is an equation obtained by adding one of the equations, or a multiple of one of the equations, to the other equation. The most common term for this is elimination. As you will see shortly here, we'll be eliminating one of the two variables. So here are our steps, and instead of reading through them, I'm going to do an example with you as we use these steps. So solve this by linear combination or, again, elimination. So first we arrange the equations with like terms in columns or vertically. So here the x's are on top of each other, that's good. The y's are on top of each other, that's good. And the constants are on top of each other, that's good. The like terms are aligned vertically in columns. Next, we look for create coefficients that are opposites for one of the variables. You might have to multiply one or both of the equations by a number to create opposites, if necessary. But here, so like 6x, the opposite of 6x is negative 6x. And unfortunately, that's not a negative 6x down there, so we don't have opposites here. But the opposite of positive 4y is negative 4y. These are opposite variables. So I have them right here. I don't need to do any multiplying for any equation. So now we add the equations, and one of the variables should cancel out. Yes, when I add the top equation with the bottom equation and combine like terms, the y's will cancel out here. So watch, here's 6x plus 3x is 9x. Negative 4y, or excuse me, positive 4y plus negative 4y is 0y. And then I add the constants together too. 12 plus 6 is 18. So now I can actually solve this equation for x. Because this 0y we don't need to write down. There are 0 y's over there. It's meaningless. We don't need to talk about it. I mean, there's also 0 a's, 0 b's, 0 c's. That variable is eliminated from this equation. Eliminated. So we can now know what x is worth, what x equals. X equals 2. Now I'm going to circle that. That's important, but that's not my solution to this system of equations. Recall when we graphed the system of equations, the solution was an intersection. It had an x and a y. Well, now I have the x. So I'm going to solve for the remaining variable. I'll substitute this answer I just solved for the remaining variable, which was x here. Now I'm going to substitute my solution into one of the original equations, either this top one or the second one, to solve for the other variable. It doesn't really matter which one you use, it's your choice. I'm going to use the top one. So I'm going to substitute in 2 for x. So 6 times 2 plus 4y equals 12. See how I just substituted that into that top equation. Now we get 12 plus 4y equals 12. We solve for y. We get 4y equals 0. So y is going to equal 0. So our solution is x comma y would be 2 comma 0. And we can check that to make sure it works in both equations. 6 times 2 is 12. 3 times 2 is 6. And I didn't mention the y's because I'm plugging in 0 there. So it is a solution to both equations. That is the correct answer, or the solution to the system of equations. So let's try that process in a few more cases. So arrange the equations with like terms in columns. We got the x's on top of each other, the y's, and the constants. Look for or create coefficients that are opposites for one of the variables. Well, the opposite of 2x is negative 2x. That's not what we have here. The opposite of 4y is negative 4y. That's not what we have here. We need opposite x's or opposite y's. We can multiply either or both of the equations by anything we want to. But if I'm going to multiply the top by something, I have to distribute that to every single term in this equation. So the opposite of 8y is negative 8y. So if I multiply this top equation by a negative 2, I'll get a negative 8y up here, which is opposite of that. So I will create opposites now. I even need to multiply or distribute that negative 2 to this negative 20. So this equation now becomes negative 4x plus negative 8y equals positive 40. Remember, when I multiply by a negative, all the signs will become opposites. So positive went to a negative, positive went to a negative, negative went to a positive. Now the second equation, I don't need to multiply anything by because I already have created opposites. So I'm just going to rewrite it so the variables are on top of each other. So negative 5x plus 8y equals negative 4. And now I'll add the equations together. So I get negative 9x plus 0y. So I'm not going to even write that down. These y's have canceled out, equals 36. So I can solve for the remaining variable. Oops, divide by negative 9. So x equals negative 4. Now that I know what one of the variables is, I'm going to substitute that value in for that variable into one of the original equations and solve for the other variable. I'm going to use one of the original ones. The numbers are smaller here. It's just a little bit easier calculation, and in case I made a mistake over here, I'm not using an equation with a mistake. So I'll use the top one just for the heck of it. So 2 times negative 4 plus 4 times y equals negative 20. That was me substituting into that top equation. So we get negative 8 plus 4y equals negative 20. Add 8, add 8. 4y equals negative 12. So that means that y equals negative 3. So my solution to this system of equations is negative 4 comma negative 3, x comma y. And mentally, I'm going to kind of double check this into this equation. Negative 5 times negative 4 is positive 20. Positive 20 plus 8 times negative 3 is negative 24. So I have positive 20 plus negative 24. Yeah, that will equal negative 4. That's a solution. And it's also a solution up here as I check that in my head. Good. There's my solution. The last thing that could add some difficulty here is it's still the same process. I want to use a linear combination or elimination to eliminate one of the variables. Here, as we look at opposites, I think I'm going to need to multiply both equations by something to get opposite variables. So, for example, I can't multiply 3 by anything to get negative 4. I can't multiply 2 by a whole number or an integer to get 5. So I'm going to have to do multiplication on each equation. So then we're going to look for the least common multiple. And we could either do this for 3 and 4 or 5 and 2. It's really your choice. Sometimes it's easier to find a least common multiple for a set of numbers, and it's more difficult for another set. So then that might determine which variable, which coefficients you want to work with. Here it's kind of a horse apiece. So the least common multiple of 3 and 4 is 12. So I want to create one equation with a positive 12x and one equation with a negative 12x. So I'm going to multiply this top equation by 4. That gives me a positive 12x. But I also need to distribute that to everything up here. So I'll get 20y and 24. Down here, so to get the opposite of a 12x, that's a negative 12x, I'll multiply this one by 3. That gives me a negative 12x. All right, we got opposites. But make sure we distribute all the way through. So we get 6y equals 5. So now we add like terms, create one equation. So this cancels out now. We get 26y ooh, I made a boo-boo. 26y equals 39. Notice how I forgot to multiply that 3 by 5. So this should be a 15 right here. So now we're getting y equals 1.5. So I'll circle that, but again, we haven't actually solved the solution to the system of equations. We need to substitute this back into one of the equations to solve for x. I'm going to use the bottom one, and notice that I have a decimal of 1.5, and multiplying it by 2 will make an integer, which is nice to work with. So we have negative 4x plus 2 times 1.5 equals 5. So we have negative 4x plus 3 equals 5. Subtract 3. Negative 4x equals 2. So x equals negative 1/2, or negative 0.5. So we put it together. Our solution is negative 0.5, comma 1.5. I'm going to plug that back into this top equation. We get negative 1.5. When I take 3 times negative 1/2 plus 5 times 1.5 is 7.5. When you combine these two numbers, you get 6. That is the solution. Last example here. So again, solving this by combinations or elimination. So if you think about what's the least common multiple of 8 and 5, that's going to be 40. So we're going to get some pretty big numbers. Whereas the least common multiple of 3 and 4, again, is 12. So I would multiply this top one by 4. So I get negative 32x plus 12y equals negative 84. Now, we got to pump the brakes a little bit here. Now I have a positive 12y on top. I want a negative 12y on the bottom. So I need to multiply this by not just 3, but a negative 3. Because now I'll have a negative 12y sitting right here. But let's make sure we distribute this to everything. So we have 15x and a negative 18. So now we combine the like terms, add the equations together. We get negative 17x equals negative, let's see, 94 negative 102. Divide by negative 17. That's going to be x equals 6. So now that we know what x is, let's go back and find y. I use the bottom equation, negative 5 times 6 plus 4 times y equals 6. So we get negative 30 plus 4y equals 6. Add 30. We get 4y equals 36. So y equals 9. So my solution, I think, is 6, comma 9. Let's double check that in the top equation. Negative 8 times 6 is negative 48. Plus 3 times 9 is 27. Add those together, you do get negative 21. Checkmate. All right. So those are some examples of linear combinations. If you want some more examples, you can look at